Great. Okay. Yeah, so now I can see your screen, and I think I'll have to introduce you before you begin to, to present. So please first stop sharing, and then I can make an introduction. Thank you very much. Okay, so hello everyone. So sorry for the delay. So there's some technical problem just being. Hello. Okay. You're still letting me in. Okay. Okay, so you can mute them and. Okay, so hello everyone, and welcome to the ISAC webinar series. So this is. Today we are very honored to have Professor Gerhard Fettweis to be here as our speaker. So before we begin, I would like to introduce the biography of Professor Gerhard. So Professor Gerhard Fettweis received the PhD degree under supervision of Professor H. Mears from RWTH Aachen in 1990. He has been a Vodafone Chair Professor with TU Dresden since 1994 and head of Fachhausen Institute since 2018. So he has been He has worked in IBM research, and he coordinates the 5G Lab Germany and has coordinated 2 German Science Foundation centers at TU Dresden. So in Dresden, his team has spun out 17 startups and set up funded projects in volume of close to euro 0.5 billion. So in 2019, he was elected into the DFG Senator. His research focuses on wireless transmission and chip design for wireless IoT platforms with 20 companies from Asia, Europe, US sponsoring his research. He also serves on the board of National Instruments Corporation and advises other companies. He's a co-chair of the IEEE 5G Future Networks Initiative and has helped organizing lots of IEEE conferences, most notably as TPC chair of ICC 2009 and TDM 2012, and as a general chair of VDC Spring 2013 and the date 2014. He's a member of the German Academy of Science, the German Academy of Engineering, and received multiple IEEE recognitions, as well as the VDE Ring of Honor. So before we start, I would like to announce a bit of news of the ISAC ETI. I would like to let you know that the ISAC Focus, which is the quarterly newsletter of the ISAC ETI, is now officially established. So in each issue will include some articles on the technical aspects of ISAC, and the video interview and some industrial progress. And also there will be advertisements on CFPs, events, and job openings. So our first issue is expected to be online this September, so please stay tuned. And I would like to remind you again the Q&A rules of our seminar. So all of you will be muted during the seminar, and please type your questions and send them to me. And we will collect questions from both audiences from Zoom and our offsite live broadcasting. During the Q&A, we will choose 3 to 5 questions to ask the speaker. And questioners will be named and are encouraged to ask questions by themselves. Okay, so Gerhard, I think I'll hand over to you. And please go ahead. So you can unmute yourself.
Yes, great. So thank you, Fan. And welcome everybody. Talking about joint communication and sensing, a topic that is of course big, and I think it's growing even bigger. something I also mentioned already a couple of years ago, that we really should do joint communication sensing at the IEEE 5G Summit in Dresden in 2019. And many others have been working on this area for quite some time. And that's why I'm happy to be participating here and giving you my point of view. I just also want to mention that we do have the symposium. Of course, it was online this year, but it will be in real life next year, coming up on this topic of joint communication and sensing. And it will be in Snowden, Innsbruck, Austria in the second week of March 2022. So stay tuned to find out more about that. Shows you that we have a lot of momentum around this area of ISAC, and that really things are happening. By the way, in the last symposium, the average attendance time was 14 hours, even though the whole symposium only took 2 days. So that's why it's really a topic that people are interested in. Let me now talk a little bit about the background. Why is this such an important topic, and where do we come from? If we want to move to the next stage, to the next step, we have to think in terms of learning from the current. And learning from the current means we really have to try to understand 5G, what it's good for, and what are the limits of 5G. And to do so, we have a couple test beds. So the red ones are test beds that we run. Like the 5G agriculture one is in the vineyard and in the orchard, on the field, etc. So it's at least 10 different installations that we're setting up right now. A couple of them are up and running already. I'll show you some pictures. And we're really learning about the application of the tactile internet, of remote control, of network controlled objects being run via the cellular network. That is the big step forward of 5G. And we see this is a functionality step function. And by doing so, we have to learn a lot from there. So there's one which is called Forschungsfeld Lausitz, that's German, of course, the research area in Lausitz, and we're in Welzow, in Hoyerswerda, and some other places, not far away from Dresden, where I'm situated. And here you see we do driving, we do flying, we do construction, and all kinds of different nice, fun areas where we're learning about how to use these kind of robots run and operated by a system, by a network that is 5G. You see one of them, the areas is there in the middle of that industrial park. The other one is on the right-hand side in Welzow, is right at the corner. Behind it, you can see an open pit mine, a big coal mine in Welzow. So it drops by a couple hundred meters behind us. And you see all kinds of different partners that we have here that collaborate with us. And the idea is, in the end, that you can run and build a building, so it is a construction site, with a lot of help by automation. That doesn't mean we get rid of people, of course, but it means we do learn how to do this with a lot of automation. And automation means, yes, you also have to do simulation. You can see on the right-hand side this little video playing of the simulation of how to operate an excavator, and to really see that you have all the tools and everything available such that we can have these kind of digital construction sites. In the agricultural domain, obviously, the future is that the tractor has no cabin, and it operates jointly with a whole fleet of others in some kind of a conjunction of others, like tractors or harvesters or whatever all. And here you again see a ton of partners that are involved. And it's not only about, of course, the remote control operations, but it's also about connecting the cows,
recording in progress,
etc., etc. So this means we really have a lot of different situations. By the way, the recording just started, so I want to welcome everybody that joins us now. And we look at the different applications areas, and it turns out it's really interesting because this is truly, in a sense, something that covers multiple aspects of us researchers in communication society, because it's about ultra short range, mid-range, long range, and ultra long range communication. All need to be coordinated and synchronized in such a way that you can cover the needs of the future of agriculture. And why is agriculture one of my pet projects? Of course, is because if we have the right sensing in place and we have the right operations in place, we can what? We can optimize when to water, where to put down fertilizer, not swamp the whole field with fertilizer. You can detect, of course, some issues and quickly use, of course, some helpers against some issues so that you can also only, you have the chemical pollution minimized by doing so. And fourth, so that all is great. That increases, let's say, the productivity, and that reduces the amount of water, chemicals, and others that we need, fertilizers. But so that's the one side, but then you can cover the whole logistics chain, not only from the field to the market, but you can also point and harvest, pinpoint the harvest exactly to the optimum ripening point. Because right now, obviously on that kind of a field, what you do is at some point in time, the farmer says, okay, the field is ripe enough, let's harvest it, or the orchard, the apples. But some apples are, of course, you've harvested them too late, others too early. So it's not really optimal in terms of productivity. But if you then have this kind of automation, you can go through the field for a month, and the harvesting period doesn't have to be one single day, but you can actually go to the orchard or the vineyard over some time and do the harvest such that you can optimize it. And by doing so, you can show you can get at least 30%, sometimes up to 100% more productivity, because we waste a lot of food right now from the field to the market because things get bad or were picked too early. This means we really need a complex, interesting complex system of all kinds of different network components that collaborate with each other, such that in the future we will have like these picking robots on the top left. We'll have harvesting systems, of course, where you harvest the grain field. On the bottom left, you see the situation in a vineyard. And here you see some photos of us really in action doing this and learning a lot about how we do this. Of course, our tractor right now still has a cabin on site, but there's no human in there. There's also cameras and everything involved, and looking at this whole system. And of course, that is just one area. The other areas is campuses and factories, etc. So this, I think, is exciting because we learn a lot about what we came up with. So we basically, as researchers, as the community, have come up with this 5G idea. And now we have to eat our own servings and trying to understand how good is it and what is the deficiency. And we can see that in all these applications, we need a ton of sensing. And that's why it's really important to look at what is the next step to make really this kind of a tactile internet happen. Where and how do we get all the sensors that we need to have this? Of course, I get a fantastic support by a bunch of companies that support us with 5G Lab Germany, and I want to say a warm thank you for that. So that was sort of the little bit of the intro. Let's put this together. 5G, that's where we're now, here right at the beginning of 5G. But we had some generations before that. We had the 1G and 2G generations where it was about telephony. Cellular communication to deliver tele-voiced services. Then we came up with a grand idea of saying, let's make the internet wireless and wide area network accessible anywhere. And with 3G, we had that introduction and had this all the way to 4G. So if you look at this, 1G was voice, 2G as well, 3G broadband data, 4G as well. So why do we need 2G? Why do we need 4G? If 5G is remote control, why do we need 6G? The interesting part, though, however, is that 1G was mainly addressing business customers. 2G made a consumer custom, a consumer product. 3G, again, the BlackBerry Nokia communicator, if you remember those days, initially those were not for consumers. Those were business people that could afford that. And only then, with 4G, did it really become a broadband consumer product. Of course, I'm oversimplifying here a bit, that's clear. And 5G, if you look at all the test beds that I showed you, agriculture, manufacturing, logistics, construction, health, whatever, we're all setting up and having fun with. These are vertical industries. So we're talking about rolling out 5G functionality for business customers, not for consumers. And only with sorry, with 6G, we have a chance to really address the consumer. Is that it? But what would the consumer really want? Now let's think of our life today. Here are just some quick examples. Your golfing machine, your Peloton, or your tennis ball machine. These are basically stationary systems that you set up and then you play with them. But how fun would it be really to have games, sports, fitness stuff that allows you to move around and not just sit in a box? I mean, during a pandemic, most gyms were closed. So even then, during a pandemic, that would be much nicer to have this kind of situation. That touches, of course, the first touches any age group, from small to old. Then as we grow up from being kids, become grown-ups, we would like to have all kinds of helpers. Cleaning up our floors, doing automated kitchen. Here's some examples. The left is a robot that we built ourselves for our test beds. The right, of course, is the Thermomix. And here you can see it would be nice to really have this kind of a situation somewhere such that we can have our kitchen fully automated and whatever. And finally, when we become physically impaired, we would like to have also, of course, our helpers. This is a picture I took myself from a Vodafone booth that we had a couple of years ago at CeBIT. And this person is paralyzed from his belly portion downwards, and he could stand up with exoskeleton. He can use his crutches still. He still needed the crutches to walk around, but sooner or later we're going to have this. Now, if we have these kind of systems, they have to be networked, because this becomes a great tool, but you can harm others because you become a Superman. And that means it needs a ton of sensors and connectivity to make sure that it doesn't accidentally run into glass doors and crash them, doesn't accidentally run into other people, doesn't fall down the stairs, etc., etc. You have to look around corners, meaning you have to be connected. You have to have all the sensing of planet Earth. If we take this kind of a vision, that means it really will revolutionize any stage of our life of the future, as kids, as grown-ups, and as elderly or impaired. Now, where is one main deficiency that we can see today? Obviously, it is the way we do network slicing. Network slicing is super expensive. You buy your network slice to go, for example, at 50 kilometers per hour, 35 miles per hour, travel through downtown, whatever city you live in, and the chances of you traveling at 50 kilometers per hour during that trip they're very minimal, because you only travel at that speed on stretches where there are not too many other cars, and where obviously you're not turning, you're not standing in front of an intersection waiting for the light to turn green and things like that. So, but what 5G does is you have to allocate your network slice the whole time at the maximum performance. So you're paying for 50 kilometers per hour, even if you're waiting at the red light. So the latency requirement while we're turning into the driveway, etc., and the reliability requirements are very different than if we're whizzing along on the street. That means we really need to make sure that we build this into a dynamic kind of system, such that we don't have this big beast sitting there the whole time, but we have something way more flexible, and have also smaller hardware for that, of course, and only call the performance in those situations when needed. And then we can easily get at least 90%, if not even 99% of the cost down. And then we're talking about making it a consumer product. So 6G, one of the main issues will be cost reduction. Why? Think of 3G. When 3G was introduced, you paid €2.50 for a minute of video call and 19 cents for a minute of voice. So who did video? If it was more than 10 times more expensive than voice, nobody did. It was a failure. It only became possible when the cost down was big enough. So here again, we have to make sure that we get the cost down big time and make these kind of ultra reliable low latency applications accessible at a level that makes sense. So now let's have a look at that first, and what is the challenge here. And so if we are interacting with the real world but remote control, then we know we need this 1 to 10 millisecond latency. Otherwise, we don't have a nice feeling. However, we know, of course, I can build a model of the human, a model of the robot, a digital twin. Yes, I can model the kinematic behavior of the real person and the kinematic behavior of the robot. And these models I can exchange and send the human's kinematic motion model to the robot and the robot's model to the human. Now, if I have these models locally available, I know based on the robot's model as a human what the robot will be doing in the next couple milliseconds. So that means I don't need to interact with the true real robot anymore, but I just interact here at the 1 to 10 millisecond with the model, and have to make sure that this model is synchronized with the real object, and this model is synchronized with that real object. But this is a completely different communications problem. This communications problem means we can actually have these guys synchronized and communicate here at way higher packet error rates, way lower requirements in terms of latency performance, etc. We can relax things big time. And this is important because the whole concept of joint communication and sensing, or integrated sensing and communications, means we have to understand this also from the application domain, and what are the requirements here, and what do we truly need, and what are these situations that really call for this kind of application. Let's dive into some details here. A couple of my team members that we want to talk about some more detailed kind of scenarios. So let's talk about the situation of a typical sensing and communication situation, which is string stable platoons. If I look at this, I have a car, the lead car, and the following car is following it, and it doesn't have cruise control, but adaptive cruise control. Adaptive cruise control means its radar detects the velocity of the car in front of it and changes the velocity of this car accordingly. And the following car does exactly the same thing. Now we know, of course, that if these cars are too close, and then we have some situation change here, then we have some chaotic bit buildup and the cars crash into each other. This happens on freeways regularly, with humans doing basically what the radar system does here. So we have to keep the cars at a reasonable distance for this whole thing to be safe, or for this to be stable from a control point of view. If we then, however, are able to communicate, we can make this more stable. Now, what is this where we have radar and communication jointly here in an integrated system fashion? How do we build these kind of systems? If we look at that, that means we really have to understand what are the requirements on this communication part. And for that, the maximum allowed time interval, the MATI, for platoon stability has to be understood. Now, what is the MATI? The maximum allowed time interval is basically tells us what is the interval at which I need to communicate, and it turns out it's also the latency at which I need to communicate. And if we have this kind of a system, and we have a sensor-only platoon, what we can see here, the first car is slowing down from 120 kilometers per hour to 117 kilometers per hour, so in 2 seconds time. So it's a very slow deceleration. And that's what the first car does. And the 10th car, this yellow car at the back, is really oscillating back and forth like crazy and banging into the car and around it. So if we were to build this kind of a platoon setup, we then really run into a challenge. If we, however, can take the same setup and have them communicate the velocities, this first one can communicate right away, and by doing so, I can make the whole system stable. But now the objective, of course, is not only to communicate the velocity, but I have a state space platoon model of the car. I have the radar sensing information. I have the wireless link. I have the preceding car and the following car. And this becomes sort of a connected kind of control system. What is it that I have to look at in terms of methodologies to really build these kind of stable systems? The one thing, of course, is the frequency domain analysis. This we know from control theory. You have to do this and see that the poles are in a region of stability, and there we go. The second part, however, is something that has been missing in this whole area so far. That is, we need to apply something called stochastic switching systems theory, which means the car sometimes does have the information of the preceding car, but sometimes a packet is lost, and then we have to rely only on the plant model of the preceding car that we have had with the model predictive control, and predict the behavior of the preceding car, and based on that, react accordingly, just like I was showing with the human and the robot before. So we have both cases. In both cases, we're using model predictive control. We're exporting the model of the other car to each other. In both cases, we're predicting, but in the one case, we get updates every time interval, and the other case, we lost the packet. And this is the system switches between these two states. And the interesting part is that stochastic system theory can show that this can be an unstable situation. If this is stable enough and the probability ratio is the right between the left and the right state, I can still build a system that in total is stable, even though one of those two states is an unstable point of operation. And of course, we have to build a very nice kinematic state estimation model of the cars, such that we can hand this over to the following car, so that the preceding car actually gives that to the following car. Then the next item or next issue that we have to look at is we have to see what does this mean in terms of impact. Here in this blue box or framed box, what you see is something from 3GPP. These are the performance requirements as of 3GPP for platooning. And we see an end-to-end latency of about 10 milliseconds. And that's what platooning requires. If we, however, do model predictive control and apply stochastic switching theory and look at what we really need in terms of packet error rates and latency. Let's have at the latency the first. And what really is important is there to look at the so-called headway time. So a headway time of 0.5 seconds means half a second later, my front bumper will be there where the rear bumper of the preceding car was at the time of measurement. Yes, so they're a half a second apart, the cars. So if you're traveling at 10 meters per second, that's around 25 miles an hour or 35 kilometers per hour. At 10 meters per second, that means these cars are 5 meters apart. The distance between the cars is 5 meters. So they're pretty close. And what we know, we need around 10 millisecond latency. But what we can show with this model predictive control and stochastic switching theory, depending upon the parameter setting, we can easily go to 100, 200, some cases even to 500 milliseconds. Nutty. So we can relax the latency dramatically. And that means me, myself, I that went around 12 years ago and talked about the tactile internet and the millisecond. I'm trying to now show that, yes, we do need it for industrial environments and whatever we're learning in the test fields, test beds. But for plenty of the consumer applications, we have to be smarter. We're engineers, we know how to build these systems. And if we look at this in the case of the packet error rate, the 99.99% packet error loss can be relaxed by 2 orders of magnitude. That means we're at 1% packet error rate, and this is something very different in the wireless communication than at 99.99%. Now, you can understand we're sensing the distance with radar. We're communicating this with a space, with a model predictive control and exporting the models of each plant to the other. And jointly, then we can attack these kind of systems. So really understanding this from an integrated sensing and communication problem means we have to deep dive into the applications to understand what is necessary. And then, of course, we can extend this further and say, okay, not only does this car communicate to the following car, and we have to look at this state space model, and we have these errors, and we only have to communicate the offset of the true versus the model, the prediction that is happening here. But we also connect, of course, the preceding car to 2 cars down and make this more stable, like a chain that is normally just one link into the other, but you can have this double link chain. That's way more stable. And then you can improve the performance even further. Now, if we go and take this one step further, we would like to, of course, at some point in time, go into the air. We want to leave ground. And that is a huge additional issue. This I do jointly with the Vodafone chair and the Barkhausen Institute. What is the problem? The problem is when we go into the air, we're not talking so much about big airliners, but drones and glider planes, which have a very similar problem, and winged drones and winged glider planes. They're fairly lightweight. So if turbulence arrives, I have to make sure that I'm not banging into the mountain, banging into the trees, or whatever else. So I need to sense what? I need to sense the wind. I need to sense the wind. Now, I have a problem because as an object in the air, I have a 3-dimensional position and a 3-dimensional orientation. That's already a 6-dimensional problem. The wind is a 3-dimensional velocity vector coming from a certain angle of arrival. And jointly, this gives me the true wind and the wind that there's of course a difference between the true wind and the wind that the aircraft sees, because the aircraft has its own velocity. And then of course I can look at the turbulence of the wind, which means I need to have the first derivative of the wind velocity. I need to know the velocity of the object and its accelerations, which is another 3 dimensions for the velocity, 6 dimensions then if I include the accelerations. So I have a fairly complex multi-state estimation problem that turns out to be not truly linear. And this is also the problem that in the end, you want to find out the wind is arriving here at this wing, and I need to know exactly the angle of attack. Because if the wind arrives here, I want to know how is this aircraft or the drone being thrown around in the air. But at the same time, the angle of attack is what determines if the aircraft still can fly or if it crashes. The mismatch between the angle of attack, measured angle of attack, and the true angle of attack was the 737 MAX problem. So the angle of attack is a true problem that can lead to disasters if you don't have a solution for that. And how it is being done today is using magnetometers. So yet another sensor, magnetometer in here, and you measure the Earth's magnetic field, and this 2-dimensional piece of information makes your estimators possible. Now the problem is what happens in small aircraft like this or like this, we cannot rely on the Earth's magnetic field. Why? Because obviously the drone is picking up a packet and there might be a metal piece in that package. And this metal piece completely distorts the magnetic field, and by so magnetometer in the drone has no chance to get the true magnetic Earth field. Same thing happens in these planes. They're full of plastic, wonderful, but the human gets inside and puts up their phone, their iPhone or whatever, or their iPad. And once you set that up, the magnetometer sees something that is not really the true magnetic field. So we have to do this without the sensor of the magnetic field. And we've been able to build a truly stable system, which is an 18-state nonlinear extended Kalman filter, such that we can have this kind of a plant model, and we can precisely measure the wind and the wind turbulences. Here's some flight paths that were flown by test pilots with our equipment inside. And we implemented this in a little unit from LXNAV on an ARM core that is sitting here inside. And it actually works. We've been the world champion in gliding, has been using this since almost a year, is totally excited about it. And yes, so this is now available for glider planes. And now the next step is, of course, to see how can we get this into drones. And if we then look at the drone problem, we also have to think of drone formation, because obviously we now have to build drones that do maintenance control of power lines, of train lines, of whatever all, continuously or after some kind of major disaster anyhow. So the question is, we have to keep these drones in a very precise formation, because their sensors and cameras are sitting here and looking at the situation. And of course, you want to build with imaging and vision algorithms some kind of analysis, and for that the formation has to be as stable as possible. So they have to communicate with each other and communicate with the ground, which should be, of course, a cellular network here as a remote control. And to make this happen and truly make this available, this is, of course, a big issue on its own. We have to make that system happen. And that's what we're working on right now. Here's some publications and references just for you. And in general, what you can see is the goal is to relax the latency from 1 millisecond to 5, maybe to 50, maybe into 100 for consumer applications and even some business applications. And of course, the reliability, relax it completely so that we don't have this ridiculous reliability that I preached 12 years ago of 10 to the minus 6 or more or less, but have this kind of system. In the end, what will we have? We will have, of course, networked robotic devices that interact with humans or not. They could be interacting in a guided surgery with humans or not. These network control devices have a ton of sensors, radar, etc., lidar, and other kind of camera sensors sitting in here. They do a lot of sensor pre-processing. And this sensor pre-processing means we have a lot of AI pre-processing. And this AI sensor pre-processing then has to be fused to really organize the total situation, which means obviously that we can expect that the networks of the will in future really will be loaded, not anymore with videos, but with these AI pre-processed data snippets that are whizzing through the air, such that the AI pre-processed sensor information of the preceding car is also sent to the following car, etc., platoons going around corners, etc., that we really have this kind of inversive environment. What does that mean for us as radio people that I am, and a little bit of control person? This means we really have to look at what sensing is necessary for these kind of systems. And the sensing that is necessary and that has been addressed with 5G is, of course, a lot of them, right? I mean, we can hear, we can see, we can touch, we have kinematic senses, and we have all these senses that we have addressed. But what we really haven't addressed so far in 5G is that we need the ambient cognition, because all these objects I was talking about need to know what's happening around them. We need this ambience. And if we have this ambience, this means, okay, we need to echolocate, we need to smell, and we need to taste. That sounds weird, but that's what we do. We use our nose. When we walk into a room and see is the situation, is there a gas leak in the room and get out again or whatever. So we need to, our eyes are echolocating the whole time. So we could use cameras, but for privacy reasons, we will not be able to use cameras. You don't want to have your vacuum robot fully equipped with cameras and upskirting you while it's driving around. So these are things that are not possible. So that means we need to look into other ways of sensing, meaning radio sensing. Radio sensing means, for example, you're driving in the car and tumbleweed comes across, or this can be foliage and fall, and the wind blows the foliage into the street. What happens is your radar sensor detects this and you come to a full stop. The car has an automatic braking system and it comes to a full stop and doesn't want to move. You as a human can crawl through here. And if there's foliage flying through the air, you can drive through this. So this is not a general challenge. So what is the problem? The problem is it's missing spectroscopy, because we want to basically, this piece of tumbleweed that is flying across, we want to make sure that we know exactly, is this a human, is this an animal, or is this just dead wood? And so we need materials analysis for that, and this is spectroscopy. So we have to do a spectroscopic image scan in addition to finding out how far it is away and where is it moving. Same thing happens if we want to do gesture detection. If we want to do gesture detection, for example, for all kinds of different things, certainly for virtual reality and augmented reality to pick up, we don't want to wear these gloves and have the sensor gloves and get sweaty fingers, but we just want to use our hands as is. And if there's a plant behind me and it's waving in the wind, that should not deteriorate the performance of my gesture detection sensor. So I need to also do materials analysis of the hand, spectroscopic scan, to make sure that I have the right thing. That means we need way more spectrum for something we today call radar, and you need to beef up radar to do also spectroscopy. But we have an issue, because today radar hogs 5 gigs of spectrum, and typically cellular in total hogs 1 gigs of spectrum. This is handed out for free to the 1% of the population that can afford a car with radar. And there, for this year, we have to pay dearly every month. In Germany, it's around €3 a month that every consumer pays to basically pay for the license fee. And this is done by 99% of the population. So everybody, no matter how rich or poor they are, have to pay for basic services. And the 1% richest get 5 gigs of spectrum for free. That's why you see this little Robin Hood here. That makes no sense. That is absolutely a terrible way of treating us. Also, obviously, I'm in the lucky position that I have a car with radar, and my radar has already stopped a couple times functioning, alert, too much activity around me. So there were too many black limos around my car, and they were jamming me with their radar, and the radar didn't function. Even though if you look at the spectral efficiency of radar, it's super low. Why? Because you need a fairly good SINR to really get a good radar image. And the radar built by Denso, and the radar built by Bosch, and the radar built by ZF and Conti and whatever all, they all are individual, because all you need to do is you send out your chirp, your impulse, and then you listen to your own reflection. And so there's no standardization, because everybody can use their own signaling, because you only talk to yourself. You don't talk to anybody else. So what do we really need is we need more spectrum for this, and we need more spectrum for communications. So currently they're fighting each other, these communities, and we really have to look at this in a different way. We're both in it for the same game. The radar guys, the sensing guys need a medium access control, because if I had a Mac, I could tell the other sensors to be quiet because I need some information, and everybody gets their fair share, and sensing is then a service. So that's why the whole idea is that we really truly build one integrated physical layer, radio access network, that does truly join communication and sensing. And this is something we need, because if we start equipping consumer devices with gazillion radar systems, because that's what we need to do, it's going to be just, even if radar goes down in price dramatically, it's going to be expensive, and we need space for that. However, if we can just use one modem to do both, and have a scheduler scheduling radar and communication parts, or even have modulation systems, come up with modulation ideas so that we can use one modulation jointly for both, then there we are. Think of it this way. If you wouldn't have your cyclic prefix in OFDM, but you would not transmit anything during the cyclic prefix, but just keep quiet and listen to the echo of the OFDM signal we've just been sending, we could already do joint communication and sensing and deliver data and get radar and spectroscopic information. Here's some publications, obviously, that we've done on this area. Now, why hasn't that happened before? Before we needed something, there's two reasons. One is for radar and communication to really happen jointly. We need something called a full duplex transceiver, because we're transmitting and receiving at the same time. In this kind of a signaling system up to 4G, that's pretty difficult, because we mainly had 120-degree cells, and we had this cocktail party effect, and the SINR is way too poor to do any kind of imaging. In 5G, and truly in 6G, we will have massive MIMO, meaning beam steering systems. And we can use this, of course, to increase our link budget, but also to reduce the interference dramatically. Because, of course, we're not emitting into a 120-degree cell anymore, but only into the direction that is needed. That's why I call this a whisper party instead of a cocktail party. And if we do that, that means we can geolocate much nicer as one of the sensing applications and do triangulation, not only by having looked at the time of flight, but also an angle of arrival and angle of departure. And secondly, of course, we can then point a beam in a certain direction, listen to the beam's reflection in a certain direction. And this is something we need for radar. We need the angle of arrival and angle of departure. And this means, in this case, we truly can build something where we have radar functionality. This was not possible with the systems we had before. And if we then do that, of course, we can do this with active radar packets as well as passive radar, where we just are communicating and sort of harvesting based on the communication packet, like I was mentioning before, with the OFDM example, harvesting the radar as sort of a passive radar sitting on the side. Now that means also, of course, we can build a radar map of the whole area, slowly but surely, or a spectroscopic map of the area, know which material is where. If there's a smoke cloud flying through the air or a pollution cloud, we know where it's going. Or if there's a flock of birds, we can identify this is a flock of birds flying along and not just foliage flying through the air. And the drone has to keep away from the flock of birds. So we really need this radar stuff in the base stations, not only in the terminals, but also in the base stations. And then we can see at this as there are different levels of information being exchanged between the terminals and between the network and the terminals. What would it be? On the one hand, you can exchange raw sensing data. And basically everybody exchanges the raw sensing data and then builds their own image, their own picture of what's happening. That probably makes less sense because that's a lot of data that needs to be communicated. Probably makes sense to invest a little bit in energy and silicon at the sensor themselves and do some imaging pre-processed data, and then do the fusion of the imaging to build imaging maps, spectroscopic maps, or maps as we know now, 3D maps as we know now. And if there are certain areas that are blocked by a building and you cannot build your map so precisely, then you just activate the terminals that are sitting in that shadow of the base station, so to do the probing and refining on demand. And then finally, of course, this gives us a static sort of map. And then you can build cognitive pre-processed object detection such that you can identify as a sensor, is this a pedestrian, a bicycle, a car, a bird, and then have these on this semi-static map, you have this dynamic objects zooming around. So what I truly think is we're going to have level 2 and level 3 sensing as a service available in 6G and beyond. Now, let me quickly look at the time check. Where are we in terms of time? And how much time should I still spend? No answer.
Gerhard,
Yes.
I think you can continue to talk. There's no time limit for now, but okay. It would be better to finish within the next maybe
10 minutes.
Yeah, right.
Good. Then I'll do that. So then let's have a look at what does that mean now putting this together, and how could such a radio access network system look like? I think we really have to look at this. We have to look at this from the application point of view. As I mentioned, communication control co-design. We have to understand this from a radio access network point of view to really build joint communication sensing into the PHY. And now comes yet another challenge, which is obviously we publish plenty of papers using hexagonal cells. And this is sort of your coverage in that kind of a situation. But if you look at the details, the reality looks quite different, right? This is a real world setup in Dresden versus the hexagonal cell setup in Dresden, something we published in Chengdu already 15 years ago. And so we basically have a situation that we are currently assuming building systems where life is good, but life is not so good. Secondly, we have an energy issue coming along. 2G had a couple of bits, 3G, 4G, 5G. We're increasing the number of bits that we need. And with MIMO OFDM, we need plenty of bits. And we're already at 200 megahertz sampling rate. And 200 megahertz is exactly the knee of the ADC converter. And if you look at this ADC figure of merit, this is the sampling frequency. This is the energy per quantization step that you need. This knee, this 200 megahertz, is something that silicon gives us. This has not been nudging a single inch since 30 years. It's always been at 200 megs. Wow. That means, and if we go beyond 200 megs, it's quadratic. So if we were to extend our ideas here and say 0.2, 5, 20, 200, and now the next is 2 gigs bandwidth, and for sensing, radar, and whatever we need wideband systems, and we increase the A to D resolution, and for tackling this full duplex problem, we need more bits resolution for the dynamic range. And we add more MIMO streams. The average increase in quantization steps has been around 100x. That makes sense because we also had around 100x data rate increase. And in the end, you have to do the resolution, and every additional bit that you have is around a quantization step. So this is around 2 orders of magnitude per generation, because we have about 2 orders of magnitude data rate increase per generation. However, if you look at the system that we saw before and the real life, we have a great SINR in some spots, but many not so. And the traffic demand is also very different from spot to spot. And with massive MIMO, we can address these pixels. That means we then, in pixels that the massive MIMO addresses, where we want to do radar, where we want to do communication, where we want to do spectroscopy, we have situations now where we have a very unoccupied network. Yes, because if we go back, the network load is always assumed to homogeneous and everything is full of terminals wanting to talk continuously. Real life looks different. So that means we have pixels in the area where we do not need OFDM. We can do impulse radio or zero crossing modulation with very high energy efficiency. That means if we take this, or this is impulse radio, and you can see here the energy efficiency. I don't want to go too much in the details. But what that means is, from an energy point of view, we're coming to a challenge. The energy consumption is increasing quadratically with the sampling rate suddenly. And there is no solution. The only solution that we have, however, is with massive MIMO, we're pointing our beam around. We need that for radar, we need that for massive MIMO, for link budget increase, etc. We get angle of arrival. So we're addressing little pixels. So in time, frequency, and an area, we have a MAC grid. And in every MAC grid, we don't need to use now the worst in terms of energy efficiency, meaning MIMO OFDM. We only need to use them where they are really needed. Think when you drive a car. If you're just sailing along on the freeway, your energy efficiency is very high. Then you're driving up the country road and there's a truck in front of you, blocking you from advancing. What you do, you change the gear, you spend a lot of energy, you push down the accelerator, you spend all that gasoline or electric energy, and you pass the truck in front of you, because in that mode of operation, that is what you need. And this is the same idea. So we really need to use the right gear of point of operation in the right situation, and then we can address the energy challenge. And that means in this concept, we also have to embed joint communication sensors. Oh, coming to an end. It is clear from 5G to 6G, we need to increase data rate. We have to address the latency. Many say we have to reduce the latency. I think that's the wrong way of going at it. Expanding coverage, yes, we want to connect more people. We have to have scalable solution, and we will have to look at what are the packets that are sent around. These are AI packets. But what we really have new is this area of joint communication sensing. And I didn't touch the other areas very much. So these are the new sports areas for the new Olympic Games. These are the old areas. They exist already, and we have to really do analysis and understand and do innovation to advance in them. But there's complete new areas, such that we have to have sensing, by the way, also radio sensing, to make sure that nobody's jamming us. Yes, we need a new RAN to make sure that we have radio sensing involved, because if somebody wants to stop the cars from driving, all they need to do is go to Alibaba. You can buy a radio gun on Alibaba, not on eBay, but on Alibaba, yes, and take down any kind of cellular network. So that means we really have to, when going from 5G to 6G, we have to be more intelligent than what, for example, is Samsung's view. Samsung is trying to just say we need to improve on everything. I think, yes, in part, peak data rate, why do we need a terabit already? 100 gigs would be great. Certainly what we should not do is doing energy efficiency and spectral efficiency at the same time, because I don't know how that works. For me, this is physically impossible. If I want to increase the spectral efficiency, I increase the resolution of the ADD converter, and we're at the 200 megs need of power consumption. So increasing the spectral efficiency is not an answer, I think. Increasing the energy efficiency, yes, we really have to address that. And then we have to look at, as I mentioned, trustworthiness. We have to look at integrity, resilience. We need to do joint communication and sensing. That's missing in this kind of a picture. And we really have to understand communication control co-design, which means we can totally relax on the reliability and on the latency in many applications. And if we look at this, of course, and look at this with Huawei's view, this is from ICC this year, Jianmin Liu's presentation. I again think we have to look at this and see, nope, there's plenty of other things that need to be done. No, 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 no. And I didn't put all the no's here, but we really have to be a little smarter than just saying we have to make everything faster, lower latency, etc. Good news is, as I mentioned, using these test beds, these campus network test beds, we can use these 5 years now that we should take time to really understand what is good, what is not good. Just like we did that in the 5 years in 3G. And we learned CDMA is horrible with the way the protocol was designed. So people invented HSPA, and with HSPA, that's when the smartphone started to make sense. So with 3.5G, you already have the precursor of the consumer product happening here, really picking up. And we will have the same thing here. Learning for 5 years now and really understanding what are the sensing requirements, what are the latency requirements, and all these different complex interactions, we can come up with the right 5.5G and then start preparing and building the new 6G that then has a new radio access network that truly does joint communication and sensing. Whereas in 5.5G, we probably only addressed to relax the latency and make this network slicing more dynamic. With that, I want to thank you for listening and see you.
Okay, thanks a lot, Gerhard. So wonderful, wonderful presentation. So I think I have received a couple of questions. The first one is from Professor Gang Wu from UESTC. So Professor Wu, can you please ask the question by yourself? Hello? Hello, Professor Wu, can you unmute yourself?
Yes, thank you.
Okay.
Thank you, Dr. Liu, for this sharing. My question is actually for the scenario of autonomous driving. So I understand the three scenarios provided by the Professor Gerhard, especially the one to provide better networked object maps with probing on demand. So sensing via terminal or sensing via traditional base station may be two different ways. So therefore, which is better between sensing and terminal? For example, for autonomous driving, currently we're using the lidar or 4D microwaves radar, or sensing via feedback or echo signal at original base station, that means bidirectional, or secondary base station like a bistatic radar. So which may be better?
Very good question. So if you think of it this way, if the road is empty, we do not need many sensors in a car to be able to drive autonomously, automatic, right? So we need a ton of radars around our car. We need lidar, cameras, whatever, all more of that. The denser the traffic is and the more inhomogeneous the traffic is. This means we're equipping a car with so many sensors to somehow be able to live with the situation. However, if I was able to grab a hold of the sensor information of a neighboring car, I could have a much better view of what is truly happening, because then I can look around corners. And if you think of it this way, if we then also put sensors into the infrastructure, like a radar and a lidar hanging off the intersection, every intersection gets its own radar, lidar, then the amount of sensors you need in every car can be reduced dramatically, at least cut in half. And you have a much safer environment, which for making sure that nobody is harmed. That means we need sensing in the infrastructure, we need sensing in the terminals, and we need sensing at the base stations. So, because the infrastructure meaning in the roadsides and etc. So we truly need sensing at all three levels, and only by joining that up can we get the pieces of information with the level of coverage that we need to make sure that we have this kind of situation handled fairly. If you're in the middle of, let's say, Mongolia or Utah or Nevada on some kind of a road that is basically empty in your car, two cars are coming to an intersection, you don't need much sensing for that kind of situation either, right? You don't need to look backwards, sideways, and whatever. All you need to have a little bit of car-to-car communication and a little of sensing and state space model exchange, and then you're totally fine. So I think it's a combination of all.
Thank you very much.
Okay, thank you, Professor Wu. So I here have another question from Professor Chao Shen. So he asked me to, to ask a question. He said, ask it on behalf of him because he's now going to sleep. So I will ask the question on behalf of him. So he has a question. He has two questions. The first question is, how can we characterize the performance of sensing and communication in a unified framework and by a unified model and using a unified KPI? So here, this is the first question. And the second one is about what kind of mathematical tool and information theoretical tools can we characterize and optimize the system performance, except for the comment filter, MDP, reinforcement learning? Yeah. So 2 questions.
Yes. So I think honestly, if we look at what we've been doing so far, is we've had a very much a unified approach, right? Everything is OFDMA, resource blocks, off we go, and you get your resource blocks accordingly. I think we have to leave that part, because at 3 a.m. in the morning, why am I sending packets with OFDMA today already? That makes no sense, because I mean the network is empty. So I could do even impulse radio or zero crossing modulation or GMSK or whatever, something way more energy efficient, and just grab a hold of the whole spectrum, have an A to D converter with only 1 bit A to D resolution, and then the 200 megahertz knee doesn't hurt me, because that only starts hitting you if you have to do level crossing detection. And then you have multi-level crossing detection, sorry, and we need an automatic gain control. And then you could actually build a super energy efficient system. So I think one can still look at this as a unified framework, but we have to think of this in a different way than we've done it so far. So far, we've thought always, let's just build this big machine for the highest data rate and highest spectral efficiency and just hammer that on there. Same thing will happen with sensing. So if we really want to get the highest, best sensing performance in a big traffic kind of situation, and we put everything in there and just address that and say, and this is what needs to be capable, this is what the network needs to be capable of doing, we're going to be in trouble. So we need to have some kind of a flexibility in that, and that's where I think and use the right gear in the right situation. That is sort of to address the first question. The second question, sorry, can you help me once again? The second question was?
So by what kind of mathematical tool we can?
Yes.
Yeah.
So what we have is, we have mathematical tools for radar performance. They exist, right? There are certain KPIs that you have in radar. We have information theory and communication theory for communication performance. What we don't have is, we do not understand how to bring this into one framework. And that is an open challenge. And I'd be happy to see somebody solve that.
Okay, thank you very much. So I personally have a final question regarding your talk. So actually, so we're thinking about this so-called perceptive network. So this is a new concept, right? By integrating sensing functionality into the current cellular network. So what do you think is the biggest challenge or biggest technical challenge if we are going to integrate, all kinds of this sensing operations like active sensing or backstatic sensing? So what is the biggest challenge when we want to integrate this into the current cellular network?
So right now we have, I don't know if there's the biggest, let me tell you at least 2. One is, how do we build transceivers that are cost effective? Because we don't want to bear the cost of a full duplex transceiver. And can we build a MAC and a modulation scheme to give us some leeway such that the full duplex requirements basically doesn't exist in that form anymore? So it is not only a hardware problem, it is a hardware, MAC, modulation, coding kind of joint problem. The second problem that we have is, we as communication people have been living in the world where we just assume we can fill our spectrum a lot, so with a high spectral efficiency, which generates a lot of interference. So how can we make sure that if we need very precise radar, right? I mean, like people are talking about in the millimeter range precision. Even though we're using the same spectrum for communication in a neighboring cell, So how to coordinate in such a way and to learn at which point in the area who has to be quiet for the sensor to function according to the spec. And to have that in a dynamic fashion, because if I only need a meter resolution, I don't need to require that kind of quietness on the air interface as I need if I want to be in the millimeter precision. So this kind of trade-off and how to build this kind of a system is super interesting, and it's an open question.
Yeah, so I guess the first challenge, also based on what I understanding, is that so first of all, this full duplex problem for joint sense and communication need to be resolved, right? So what we can use, as you just suggested, we can design a new MAC or something else to try to avoid this full duplex problem. And I think the second one, in my own understanding, is that in a pure communication cellular network, you can somehow to schedule the transmission, right? Schedule transmission and reception. And in that sense, you can somehow to control the whole network. But when you have this sensing functionality in the network, when you're trying to, actively sense some targets and to receive the echoes, there's no control of that echoes, actually. You don't know when these echo signals or reflections will be received, right? So that will cause interference. So that will be some interesting scheduling strategies in that. I think that is also a very interesting problem.
But I mean, the good news is in most applications, in most situations, we don't need the sensing information that from an echo that is far away. Right, so it is fairly nearby. And for the base stations that are slowly building the map of also faraway objects, they can use, of course, they can get a lot of SNR by just integrating in time, because I mean the houses don't move, right? So that means for the dynamic parts, you're right, but the dynamic parts are local, and the static parts, they are far away, but they're static. So we can actually, I think we can come up with some nice trade-off ideas to tackle that.
Yeah. Very interesting. So I think that will be all for today's seminar. And thank you very much, Gerhard, for attending. And we look forward to seeing you in our future events. And before I let you go, I just want to advertise our next event. So this is the 6th seminar of the IEEE ComSoc-SPS ISAC webinar series, which will be given by Professor Robotic. But the date is currently need to be determined, because we still need to coordinate with him about the dates, and we will let you know once we have confirmed all this information. So thank you very much for attending. So I guess that'll be all for today's seminar, and we will see you again in our next event. Goodbye and good night or good afternoon. Bye-bye.